going to be what I think one of the more practical videos in the series. So the last videos that you watched were on dynamics, but if you're programming a spacecraft, you don't actually program the dynamics unless you're doing some sort of model estimation with some sort of observer. In this case, what we're looking at is if we have sensors on board, how do we filter and average that data as best as we can. There are some very, very complex filters out there, like complex filters, scented filters, bubble filters, things like that. I'm just going to use the complementary filter. And the reason why is because it's the easiest to code. We're right now developing a 2U CubeSat, and so we're not really looking for that much accuracy and precision. And so I think that the complementary filter is going to be just fine. The end game, the equation at the end is actually fairly simple, but there's a lot involved to get there. I tried to fit a lot on one slide. Some of these words are, in my opinion, impossible to read. And so I'm going to go through this slowly, one at a time. And so this might be a fairly long video, but I want to make sure that you can make out every single thing on this chart here. And if there's something that's a little bit, even after I said it, and you're looking at it and you still can't quite make it out, just post in the comments and I'll try and help you out. Okay, so let's start with this title here. So we're looking at state estimation, so we're trying to estimate some state. In this case, we are estimating the state for Magnetorquer control. So in that case, we're trying to measure angular velocity and we're trying to measure the magnetic field. So we're in space, tumbling around the Earth. We want to know how fast we're spinning, and I want to know what the current magnetic field is. I'm going to go over how the control system works. That's this block C in a subsequent video. And so here I'm just going to show an overall video. And you've probably seen this block diagram in the first video when I went over the overview for ADCS. But in this video, I'm going to get a little bit more detailed on the sensor algorithm. So let's go through this. So this is state estimation again for Magnetorquer control. So I'm trying to slow the satellite down with Magnetorquers. Those are torque rods. So they, it's a looped current. It's a current through a looped wire that creates its own magnetic field, and that magnetic field opposes the Earth magnetic field, and it puts a torque on the spacecraft. And so we're trying to use torque rods or Magnetorquers to slow the satellite down. And I'm going to use a complementary filter here. So again, I'm saying that I want to slow the satellite down. So what I want is I want omega command. So this says command. Omega is my angular velocity. I want my angular velocity vector to be 0. This bottom block I'll talk about in a second, but basically the error signal, so this is the difference between my command and where I think I am. I don't actually know how fast I'm spinning, I just have an estimate. And actually, I'll go ahead and just mention this one branch here. So this is my estimated angular velocity. Again, I don't know how fast I'm spinning, but I have a pretty good idea based on some measurements. And hopefully this complementary filter. So that error signal, which is my command minus my estimate, is going to go into a controller. And again, I'm going to have a separate video talking about this controller. But that controller is going to compute how much current in amps, that's what I mean by current in amps, that I need to run through the Magnetorquers. So that current is going to get sent to the actuator. In this case, the actuator is whatever circuitry is actually going to create the current to run through the coils. And then that is basically going to create the moment, or the magnetic field that's going to create the moment that is going to get put on the plant. And the plant in this case is the spacecraft, and that's going to start detumbling the spacecraft. This is the truth, in this control block diagram, this is the truth signal. So we assume that there is some true angular velocity that we can measure, but we don't directly know. And so if I have a sensor, and I'm going to call it H, I'm going to measure that signal, and that's going to give me omega bar, which is my measured signal. Okay? And so my measured signal here is then going to go through my estimation block, and so that's my complementary filter in this case, but it could be something more complex. So this is my navigation filter, which is going to give me my estimate of my truth. It'd be nice if this were identity and I would have unity feedback, but life's not so simple, and so I have to have a sensor that is going to give me a measured signal, and then I'm going to go through my navigation block to get my estimate. Some systems even just don't even have a navigation block at all and just take their measured signal and run it through. But measured signals, if we jump over here, measured signals, which generally speaking we call Y bar K, and K is the kth measurement. So computers are discrete. I don't measure things on a computer continuously all the time. It seems like it's all the time, but really everything is discrete, right? So like the frame rate of this video is 30 frames per second. So it's not actually a continuous video. You're getting a frame every 30th of a second, and your eyes think that it is a continuous video. Sensors are the same thing. Every fraction of a second, you're going to get a discrete measurement, and we call that YK. And then the bar just denotes that it's the measurement. Now that YK bar is going to, generally speaking, be some function. So H is a function of X, the state, plus some noise, which we call, that's the Greek letter nu, N-U. It's not V, it's nu. And plus BK, which is a bias. So there's going to be an offset, there's going to be a random noise, which we assume that this noise is Gaussian, and there might be some nonlinear function of X. If we define some extra things here, this noise vector, we're going to assume that the covariance, and that should have the covariance of the noise vector is equal to, this E is called the expectation operator, and that's VK times VK transpose is equal to some matrix R. And so the matrix R basically tells us how much noise is in the sensor. If R is really, really, really big, it means our sensor is garbage. If R is really, really, really small, it means our sensor is really good, we don't have that much noise. The metric for this variable R is kind of a tuning parameter that the control system designer can play with. It's kind of like a gain. The easiest way to create your filter, or to create your estimate, your navigation filter, is to linearize H, the function, to get HK. The two lines underneath it, by the way, those two lines mean that these are matrices. And so if you think if V is a column vector, V transpose is a row vector, and if you take a column vector times a row vector, you get a matrix. Same thing with H. H is going to be some nonlinear function. If you take the Jacobian of it, if you linearize it about a trim point, you're going to get a matrix. Okay? And so we assume H there. Now the easiest method, and this is what you're taught in, I want to say high school, you probably don't learn it like this, but this is trend line fitting, linear least squares. And so the general form of linear least squares is you assume that you take many measurements. In this case, you're going to take n measurements, not 1, not 2, not 3, but n, okay? You need to make sure that the number of measurements is greater than the number of states. And so angular velocity is 3 states, roll rate, pitch rate, yaw rate. So if you're going to use least squares, you need to take at least 3 measurements. I would recommend take as many as you can. So the idea with taking these measurements is if you have a sensor that's really fast, say you can get 100 measurements in a tenth of a second. I would recommend doing it. Just every tenth of a second, take 100 measurements and then throw it into this algorithm. So what's going to happen is you're going to get all of the measurements that you got in that fraction of a second. And at least for this algorithm, you have to assume you know the bias. That assumes that you've taken the sensor, put it on the ground, shielded it from any external disturbances, and taken data and measured the bias. Getting bias is very hard, and there are more complex filters out there that will measure the bias for you, and that would be like an extended state common filter, an EKF, if you want to Google that and take a look at it. At least for this seminar series and for this example, I'm not going to go into that, and so I'm just going to assume that you do know the bias. You don't know what the noise is, you have an estimate of the covariance, but you don't know the noise. And so you're trying to filter that out. So you subtract off the bias from every single one of these terms and you put this into a big matrix called y bar. So this is a huge matrix y bar. So this is an n by 1 vector. If you look at this, if you take this equation, which is just one measurement, and you combine all of those equations into n equations, you're going to get y bar is equal to big H matrix, which is basically all of these h's stacked together, times x, the truth signal, plus v, which is all of your noises stitched together. Now what you're trying to do is you're trying to solve for x. The problem is that this noise vector makes this solution not solvable. So what you do, and this is what Gauss figured out back in the day, and I would read stories about Gauss. There's a lot of really funny stories with Gauss. But he invented this equation here, and this is what's called the least squares solution. Again, you may not have seen this when you learn trendline fitting or least squares regression in general, but this is actually the pure form of least squares regression. So it's H transpose H inverse H transpose Y. Okay? And by the way, all of these equations, I'm eventually going to create a MATLAB and Python code that simulates the dynamics and simulates this filter and the controller. So if it doesn't make sense right now, that's fine, we're just doing the theory. Eventually I am going to apply it and put it onto real simulation software. Okay, so again, this is the estimate of my state at the kth measurement, and it's equal to H transpose H inverse H transpose Y. Okay? All right. The second way is to use, this is just the least squares method. The second way is to use the complementary filter. So the idea is that at the kth time instant, you're going to get an estimate. Well, what happens at the next measurement? Are you going to just throw that measurement away and redo the least squares? And then when you get to the next measurement, are you going to throw the previous ones away and then just use the next one? It would be nice if, as you propagated forward, you used the previous measurement in your calculation to help you estimate the future state. And that's known as a sequential linear least squares estimator and sequential filters. And so what we assume is that in this case, we're going to say the k minus 1th measurement, the estimate, the k minus 1 estimate is known, and we're going to assume it's equal to the truth signal plus some model noise. The covariance of the model noise is the expectation of omega k times omega k transpose, and I'm going to call that Q. So we have R here, which essentially tells us how bad our sensor is, and Q tells us how bad our previous measurement was. Okay? So keep that in mind when we get to the green area. Okay, so we're going to use least squares on this. The math for this is very complex, so I'm going to leave that out. But basically what ends up happening is that you get the next measurement you get is equal to this lambda matrix times your current measurement minus the bias plus your last measurement times this gamma matrix here. And again, these are very complex matrices, so I just left them off. I don't think it's important to learn them because when you apply these to angular velocity measurements and magnetometer measurements, you end up making so many simplifications that the final solution is way easier than these matrices were in the first place, so I just leave them off. Okay? But again, the main takeaway is your next measurement is your previous measurement plus your current measurement with these two factors included. Okay? So let's see if we can dive a little bit deeper on that. So let's talk about the angular velocity and magnetometer measurement. I'm only going to do the angular velocity example because the magnetometer example is almost identical. So I'm going to assume every kth time step, I'm going to get a measurement. And that's equal to the truth signal plus a random noise plus a bias. Because my sensor, the sensor on board of typical spacecraft, you're going to have a rate gyro and you're going to have a magnetometer. And those rate gyros directly measure angular velocity. They are not a nonlinear function of angular velocity, nor are they some scale on angular velocity. In this case, whatever your angular velocity of your spacecraft is what you're measuring, plus some bias and some standard and some random noise. So that means that HK is actually just equal to identity. Oops. So that's an identity matrix, basically 1, with along the diagonal. To make the math simpler, I'm going to assume that Q inverse is S and R inverse is 1 minus S. Okay? And you'll see why I did that in a second. If you use method 1, where you take a bunch of measurements, if you look at this equation, H transpose H, if you do the identity matrix, H transpose H is going to give you N, the number of measurements. N inverse, because N is a scalar now, is just 1 divided by N. So it's 1 divided by the total number of measurements. H transpose Y is all of the measurements added up. So basically this is all of the measurements added up divided by the total number of measurements. And obviously that's the average. How do you take the average of a signal? You add up all of the measurements and divide by the total number of measurements. So if you use method 1, which is, say, every fraction of a second I take 100 measurements, if you just average them all together, you will filter out the noise. It may not be good, but you'll filter out the noise. The problem with a method like that is that what happens if the spacecraft is tumbling quickly? And if this were a perfect system, you could pause physics and take 100 measurements and then average all of the signals. But you can't do that, because in real life, everything takes time. So as you're taking data, the spacecraft is moving. And so you're trying to take these angular velocity measurements while the spacecraft is moving. And unfortunately, that's going to really throw off your data. So the better way is to use this complementary filter. And so if you take this equation, and again, these matrices were complicated, if you substitute in all of these equations and plug them into lambda and gamma, you get this equation here. So this equation here says that the measurement of my angular velocity at the kth interval, time step, is equal to 1 minus S times the measurement, so that's the measurement that comes out of the rate gyro, minus the bias that I assume I know, plus S times the previous measurement. Now, let's take a look at this equation and see what it does. If I assume S is equal to 1, it means that this whole term is going to go to 0. And so that means that the kth estimate is going to be equal to the previous measurement. And then the next measurement is going to be equal to the previous measurement. So you basically ignore your measurement, your sensor. You ignore your sensor. And so if you look at this, if S is equal to 1, right? If S is equal to 1, 1 minus S is 0. So that means that R inverse, this says R inverse is 0. If R inverse is 0, it means that R is going to infinity, right? It means that R is going to infinity. And remember what R is. R is the expectation of your noise. If you pick S equal to 1, what you're saying is that your sensor is really, really, really bad. And it's saying, hey, complementary filter, ignore the measurements. It's terrible. Remember, you, the control system designer, get to pick S. If you think you have a bad sensor, you will probably want to make S fairly large, right? Or sorry, close to 1. If you make S bigger than 1, this whole thing doesn't work. So you want to make S fairly large, okay? I said that wrong again. You want to make S close to 1. You want to make R fairly large. If you make R very big, it makes R inverse very small, which makes S close to 1, okay? If you do the opposite, if you make S 0, this term comes back and this term goes to 0. So you're basically saying, throw out the previous measurement, believe the current measurement. And so what you're saying is that S is 0, and if S is 0, Q inverse is 0, which means Q is going to infinity. And remember, Q is the expectation of your previous measurement, of the noise in your previous measurement. So if you make Q really big, you're saying that your previous measurement was garbage, okay? So you have these sliders that you could play. You could make R really, really big and say, my sensor is garbage, use my previous measurement. Or you could do the flip and you could say, make Q really, really big, believe my sensor because my previous measurement was garbage. Now, I haven't seen S change dynamically ever. So typically what people do is they make Q and R constants and then just let the common filter go. So what I'll do when I finally put this into a computer program, we will change S to different, I kind of want to use Q and R, but we will change Q and R to different parameters so you can kind of see the games that you can play when you choose say Q really, really big versus R really, really big, and you can kind of see what will happen. Okay? That was a lot to get through in one slide. Hopefully that makes sense. Again, the biggest takeaways are that you don't actually know what your truth signal is, and so you have to measure it. Your measurement is going to have some noise, some bias, and it might even have some nonlinear function of your state. For angular velocity, we're lucky, and we only have noise and bias. And so as long as we know the bias, we can subtract the bias off and then use a complementary filter to filter out the noise. Those are the main takeaways of this video. So I hope you enjoyed it. I hope you have a good night, and I'll see you in the next video.